We have spent about 6 videos talking about how to resolve vectors. So what's the purpose of resolving vectors actually? Okay, so here I'm going to give you a rough picture of how resolving vectors is able to solve a very big problem that we have when we are dealing with summation of vectors. Okay, so today let's say let me give you a situation. Today you are at home, then you happens to want to go out, but you follow the SOP as usual. You wear your mask and you go out. You walk for 500 meters to get your nasi lemak. Then after you get your nasi lemak, you change your direction a bit. Then you walk for another 200 meter. Okay, you change your direction by about 20 degree and you move for another 200 meter towards a lake. So at this lake, you might be fishing, you might be just resting, I'm not sure. Okay, but this is a situation. Okay, now if I ask you to obtain the final displacement of you traveling from your home to the nasi lemak stall to the lake, in order to obtain the final displacement, what would you do is you take the first part of the displacement, which is S1, first part of the displacement, together with the second part of the displacement. If you sum up both vectors, you should be able to obtain the final displacement, which is S. If I want to draw this S here on the picture, it probably be like this. This dotted line, dotted red arrow here is representing the total displacement or the final displacement S. Okay, so as you can see, this arrow here starts from the tail of the first vector and ends at the head of the last vector. So be very this one, please take note here. It should start at the tail of the first vector and it should end at the head of the last vector. Okay, so we know this will be the answer. If we measure the length of this arrow and we measure the angle of this arrow, that's our answer actually. But what if today we are given we cannot do it by drawing? What if today we cannot do it by drawing? You don't have a very good ruler, you don't have a very good protractor, but you only have 500 meter to the right and 200 meter 20 degree below positive axis. What if you only have these details and you are asked to perform calculations instead of geometry? How do you add up these two directions? And that is where resolving vectors come in. If we re-express the directions in terms of components by resolving the vectors, we will be able to do our summation of vectors through calculation without going through the steps of drawing and measuring. Okay? So let me do it in a more concrete way. Let's say today I have vector A, vector B, vector C, vector D, and these are the vectors being expressed in numbers and words to describe its direction. And let's say today I ask you to sum up these vectors. Okay, well, let me show you again how should we do this in a graphical way, in a geometrical way. How should we do this is we should introduce an x and y axis first. Okay, to do any addition of vector, if you're doing it using drawing, using geometry, what should we do is we should create an xy axis, then put in all the vectors into this xy axis. But if you're doing it geometrically, how should we do it is we should do it like the nasi lemak and the lake example just now. We take one vector, follow up with another vector. But in this case, there's 4 vectors. So we take one vector, followed by another vector, followed by another vector, just like this. A, followed by B, followed by C, followed by D. Okay, so we take the tail of the next vector and we connect it with the head of the previous vector. We take the tail of the next vector, we connect it with the head of the previous vector. So we continue everything flowing until here. Then our our resultant vector, our final answer will be from the tail of the first vector pointing towards the head of the last vector. Okay, I mentioned just now, remember that it's from the tail of the first vector towards the head of the last vector, right? So this is our final answer, which we say this is the sum of A and B and C and D. If you sum these 4 vectors up, this should be our final answer. And we call this answer here resultant vector. It's the result of the summation. So resultant vector, and I label it as R, meaning resultant. And of course, R has a certain magnitude and a certain direction, which can be described by the angle theta subscript R. Okay, so this is how we should do it if it's a geometrical task, if you're asked to draw and measure everything, angles, length, everything. But in our physics usual calculation, we don't usually rely on drawing and measuring, because you can't draw really accurately most of the time, and using protractors can be a little bit of a hassle. Okay, so now let's see, if you have this kind of situation, how should we make use of this information to do calculation to obtain resultant vector? What should we do? Apply the concept of resolving vectors. Let's see. Let's take this vector A here and let's resolve it. Okay, I'll remove the answer, then we see how we get the answer using resolving vectors. This vector here, vector A here, let's resolve, then it become AX. There's no AY, right? Because there's no component in the Y direction. So we can rewrite our vector in terms of its X and Y components. So AX will be positive something something, AY will be 0 because there's no AY component. Okay, for B, we can also split into BX and BY. So if we split into BX and BY, BX will be positive pointing to the right, then BY will be pointing in the negative direction. Again, for C, we split it into its parts, its components as well. So you have CX and CY. CX in the negative direction, CY in the positive direction. Okay, now it's a bit messy already. D, again, vector D, we resolve it into X component and Y component. X pointing to the negative X direction, Y pointing to the negative Y direction. That's why both negative. Now, this is the process of resolving a vectors. So how does resolve vectors help us to sum up the vectors? Now let's ignore the actual vector and look only at the components. Okay, if we do it geometrically, we only look at the components. Then let's see how these components help us to determine the resultant vector. Okay, so what we do is we bring all the X components towards the x-axis. So now I bring CX to the x-axis, I bring DX to the x-axis. Okay, then I also bring all the Y components to the y-axis. I bring BY over here, I bring CY over here, I bring DY over here. All the Y components, I collect it and I put it at the y-axis. Okay, now do you see that AX and BX and CX and DX can actually all be summed up together? Okay, if it's AX is positive, then you add on with BX, which is also positive, then you add on with CX, which is a negative, you add a negative value, then you add on DX, which is also a negative value, then you end up with an answer, which is this one, Rx. Okay, you sum up all 4 of them. You might be wondering why there's no minus sign, because the minus sign is inside the CX, inside the DX. Okay, later we'll talk more about this, but if you calculate everything, Rx should have this length over here. Okay, again, from the tail of the first component, the head of the last component. Okay, again, for Y, the tail of the first component, the head of the last component, so our resultant Y component will be this one. Okay, so now once we have Rx and Ry, if you want to get back R, it's not a very big deal, right? You just need to draw dotted lines, and we can get back our vector R, and we can also get back its angle. Okay, so this is just a graphical example to show you how resolving vectors also allow us to obtain the resultant vector. Resultant vector is again the summation of the vectors A, B, C, D. Okay, so resolving vectors can do that. I'm proving this to you using pictures. Now we are going to do the exact calculation in the next video.